So today we are going to look at the physics of a quantum Hall edge, whether integer or fractional. We already know that whenever there's a quantum Hall state with a quantization of the Hall resistivity, with a vanishing of the longitudinal resistivity, and with an energy gap in the bulk, there must be a chiral edge to carry the current. We also know that there's a simple example to see that, which is the example of Landau levels, of just non-interacting electrons. So if you just look at the Landau level dispersion under the confinement of a potential, this white line is the confining potential, you see that the Landau levels curve up, and even if the chemical potential in the bulk is in a gap, as we get close to the edge, the gap must close, and we must get gapless modes on the two sides, one moving clockwise, the other one moving counterclockwise, or whatever directions you put your sample in. We'd like to now formulate a description of these edges, write a Lagrangian, write a Hamiltonian, define the fields, and so on and so forth. We'd like to avoid a few complications to start with, and the first one is going to be that we'd like to focus on a case where on each side there's just a single edge. This is like we do here. Of course, nu equals 1 is the most prominent example of this, but 1/3, the poster child of the fractional quantum Hall effect, is also a good example that we should keep in mind and come back to. We want to have one or two more simplifications. We don't want to worry at the moment about how the edges couple to the metallic contacts from which current comes in and out of the sample, and therefore we'll put our system on a Corbino disk with no contacts. We also don't want to know about the entire disk and worry about boundary conditions, so we'll zoom in on a small part of the disk, and here it is zoomed in, and now we got to the system we would like to look at, where there's one edge mode flowing right and one edge mode flowing left. This actually looks a little bit like what you would see in a quantum wire, right? In a one-dimensional quantum wire, except that the wire does not have this bulk. So, in a wire there's an energy dispersion, and there are right movers, which correspond to these guys, and there are left movers, which corresponds to these guys. The only difference between this wire and a quantum Hall and nu equals 1 quantum Hall system is that there's a physical separation between the right movers and the left movers in the form of the 2D bulk that's gapped, and therefore scattering from right to left is strongly suppressed, and that is what gives the quantum Hall effect its precision. It's very hard to be backscattered. Now, we know from the physics of one-dimensional systems that there's a very strong theoretical tool that can help us understand such systems, and this is the tool of one-dimensional bosonization. It's useful, but it's not essential for the discussion we're going to have today, so no prior knowledge here of bosonization is needed. So what I'd like to do now is to construct a description of the edge, a description of the single edge mode on each wall system based on two premises. First, let's look at this system and describe it in terms of the edge density and edge current on each of the two edges. And let's keep also an open mind to having an electric field operating everywhere in the sample, including on both edges. So this is the electric field, and it will get the subscript edge when we think about it operating on the two edges. So what happens as a consequence of such an electric field? This is a quantum Hall system. If there's an electric field going in this direction, there will be a current flowing either upwards or downwards. The directions are not important. But there will be a current that will make charges move from one direction of the edge to another direction of the edge. From one side of the sample to the other side of the sample. That means that each of the edges is a one-dimensional system, is chiral, but is not a system that conserves charge. There is a total conservation of charge on the two edges together, but there is no conservation of charge on each of the edges separately. Now, this lack of charge conservation will be important to us in the discussion that comes now. But before that, let me say the electric field doesn't have to be the same on both edges. In fact, it can even be opposite. What happened then? What happens to charge conservation generally is something is a question I would like to leave you to think about. What I'm going to do is to think only about one edge and in the presence of this electric field. So charge conservation doesn't hold, and the equation that replaces charge conservation is this: the time derivative of the density plus the position derivative of the current, which sum up to zero if the system conserves charge, does not sum up to zero, but sums up to the supply of current from the Hall effect, which is the Hall conductivity multiplied by the electric field along the edge. So this equation is one of the two pillars on which our description of the edge is going to stand. The second one is going to be an approximation. And the approximation is that if we have an edge mode here and an edge mode here, and they have energy dispersion with respect to momentum, we are going to assume that these dispersions are both linear, and therefore that dE decay is a constant, and there's only one velocity on each edge, which means if there's a constant velocity, that the edge current and the edge density must be proportional to one another with a velocity that relates between the two. So with these two, we can now write a Lagrangian density in terms of a field chi that's a function of position x and time t. And we're going to write a Lagrangian density. Here it is on the board. And we're going to see that this Lagrangian density reproduces the equation of motion that we already know that we want. So this Lagrangian density has three terms. One term is the coupling to the electric field. One term is a velocity multiplied by dx chi squared. And one term involves the derivative of chi with respect to x and the derivative of chi with respect to t. Those three terms should reproduce for us this equation that we know should hold. How does this happen? Well, to extract an equation of motion from a Lagrangian density, we need to do the Euler-Lagrange procedure. This term will give rise to this term. This term will come out of this one, and this term will come out of this one. You see, when we take a variation with respect to chi, we'll get this. Sigma xy or yx will occur from these terms. The position derivative of the current will come out of this, and the time derivative of the edge will come out of this. And this combination suggests to us that the edge density should be proportional to dx of chi, and the current should be proportional to this multiplied by the velocity. Now, having this Lagrangian, we can also transform now to an Hamiltonian description. And the way to do that, as always, is to do the Legendre transform trick, which focuses on this term. This is the symplectic term. This is what takes the role of PQ dot in classical mechanics. And this is, as you remember, in classical mechanics, P and Q come out to be canonically conjugate to one another because the Lagrangian has PQ dot terminate. And in this case, when we do the transform to the Hamiltonian, we will find from here that chi is the canonically conjugate operator to dx chi. So there's a commutation relation of chi of x and dx chi of x. The field chi is a bosonic field, and therefore what we find is a commutation relation. So, you know, there's an uncertainty principle. You cannot define the density at the point x prime and the integral of the density up to that point simultaneously. It's an unusual situation where we cannot, or where the field at its derivative cannot be simultaneously defined or do not commute with one another. You see that sigma xy comes out of doing the Legendre transform and multiplying by what appears here in the denominator. So we see the field and its derivative do not commute, and the commutation relation encodes to us the fitting fraction we are interested in. Encodes to us the main property of this topological state, the main quantum number of this topological state. This non-commutativity of these two fields is closely related to the fact that it's a chiral system and that the edge does not conserve charge by, that each of the two edges does not conserve charge by itself. To summarize this, we can put this in a table. We saw this commutation relation, we saw the Lagrangian density, we identified the density as a derivative with respect to position of chi. The normalization, basically all these factors of 2 pi can be made to come or to go based on normalizations of the field chi. You know, we can multiply chi by some factor and make them go away, and some places in the literature actually do just that. This convention is such that a soliton in the field chi of 2 pi corresponds to a charge of an electron. And indeed, this is what you see here. So now, those two fields, or those two operators, are operators that add charge to the edge. Suppose that we want to take an edge and apply an operator that changes the total charge on that edge. If you change the total charge on the edge, you surely change the charge density at the point where you operate. So you want to apply an operator that will change this operator, the value of this operator at a particular point. And you know, in quantum mechanics, if you want to change a value of, if you want to change the value of x, you apply an operator e to the I p a, and then x moves by a. You apply an operator that's an exponent of the conjugate variable, the conjugate field or variable. So here we want to shift the value of the density. We need to operate e to the I chi times the conjugate field, which we know, excuse me, e to the I times the conjugate field, which we know is chi. And the prefactor of chi will stand like this A here, will tell us by how much we shift the density, which is another way of saying how much density, how much charge do we put into the edge. So, and the way it goes is e to the I chi with this normalization will correspond to adding a quasi-particle to the edge, a fractionally charged quasi-particle, while e to the I chi over sigma xy, let's say in the example of nucleus 1/3, e to the 3I chi would correspond to adding an electron to the system. So what can we do with this description? There are many physical situations where we can apply this description of the edges, and I'll describe one. And in this one, what we're doing is we're taking 2 points along the Corbino disk and bring them close together to allow tunneling between the two edges. Now, there may be various types of tunneling. There may be a quasi-particle tunneling because those two edges are now related through or connected through a quantum Hall bulk. And a quasi-particle tunneling operator would look like that. But then there may be also a tunneling, electron tunneling operator, and this one will have this factor of 1 over sigma xy, which basically says that an electron is just 1 over sigma xy quasi-particles, 3 quasi-particles in the case of nu equals 1/3. So the tunneling of an electron would look like that, where chi r and chi l are the fields that correspond to the two edges. Now, what effect will this type of tunneling have? It depends, of course, whether it's weak tunneling or strong tunneling. If it's weak tunneling, then there will be occasionally, most of the charges will flow around, and occasionally there will be a charge transfer along across the bulk. If we put a voltage between this edge and that edge, we will find current flowing, and there will be an I versus V dependence that in fact will turn out to be non-trivial and will be affected by the value of sigma xy. If lambda is strong, then it's a different story. Look what happens. If lambda is strong for the quasi-particle tunneling, for example, this cosine becomes a very large term. And that means that the argument of the cosine must be, at the ground state, very close to its minimum value, which means physically that when current comes in here and gets to this point, mostly it will be transferred. And when it comes from here and gets to this point, mostly it will be transferred. Basically, the edges are connected to one another, or you can almost think about this as this being torn out. And this you almost create a void here. But not quite, because electrons can still tunnel from this side to this side, and that corresponds to tunneling of the system, or of the state of the system, from one minimum of this cosine to another. Now, what determines whether lambda is large or small? First of all, of course, how close these two edges are brought to be. But more than that, there's also a process of renormalization as a function of energy and temperature, which changes the value of lambda, and which is something I will not cover in this lecture. So renormalization makes lambda depend on energy. And as you take the energy to smaller and smaller values, it so happens quasi-particle tunneling gets stronger, known as relevant in the renormalization group language, while electron tunneling gets weaker because it's irrelevant. So this is the story of a single edge mode. Now, how do we generalize it to many edge modes, to situations where each wall, each edge of the sample has several modes? First of all, let's think about examples. There could be very simple examples. For example, suppose that you have two layers, each one with a quantum Hall state, this one with 1/3, and this one with 1/5. Which also has a single edge mode, or a third one which will have nu equals 1. So each one of them will have now a different field, chi1, chi2, chi3. And each one will have different terms in its Lagrangian. Not only that, they can also live on the same edge. For example, what happens if you have total nu equals 1 1/3, 4/3? Then you would have one edge mode for the one edge mode for the 1/3. And there are more complicated examples. So we should be able to generalize the Lagrangian and the formalism that we had before for this case. And I'll touch this very briefly. So the description we have, in particular the Lagrangian density that has three terms, one coupling to the electric field, one density coupling, and one symplectic term. The identification of the density as a derivative of chi, and the commutation relation that come out of this, all those are, something needs to be left out of this when we generalize. Basically, the generalization should go along these lines. So let's see how it goes. So now in the Lagrangian density first, we're going to have each of the fields coupled to the electric field. But different fields may have different charges. You can imagine a situation where one layer has electrons, the other one has holes with charges of plus E and minus E. Maybe even more exotic. One layer has charge 1 particles, and second layer has charge 2 particles. So the coupling to the electric field should be weighed with the charges of each of the fields. Now the density interaction now does not necessarily couple only each edge to itself. This is just basically Coulomb interaction described here as a short range interaction, but that's a detail. So all charges can interact with one another, and in particular, the density interaction becomes is described by a matrix, by an interaction matrix. This matrix should be symmetric. Just look at it. It should be symmetric, and also it should be positive definite, so that the edge does not break into charged regions spontaneously. And the symplectic term has maybe the most subtle aspects into it. Also is described by a matrix. It's easy to think about this matrix as being diagonal. This is the case we talked about before. If we have nu equals 1, and on top of it nu equals 1/3, then this one will be described by a k that's 1, and this one will be described by a k that is 3, because 1 over sigma xy. So we would have the k matrix look like 1 and 3. But in fact, there may be also off-diagonal terms to this matrix, so that it's also a symmetric matrix, but it can be it can include terms which are diagonal and off-diagonal as well. I'm not getting into details of this because we will see that happening when we talk about flux attachment later on in the course. Now, we can also generalize the operator to create quasi-particles. We can also identify the charge of the quasi-particles, and there are many details to this description which I'm not getting to. I'll just say one more thing important about this description and summarize. And this is, again, I'll state this without deriving, but if we assume that the quantum Hall state has a finite set of quasi-particles from which we can construct full electrons, that translates into the requirement that Kij can be written as made of integer numbers only. If we normalize our fields chi in the way that we did before, meaning a 2 pi soliton is an electron charge, then the matrix Kij is an integer valued matrix. So to summarize, what we did today was to look at physics of the edge and to construct a description of the edge in terms of a bosonic field, a Lagrangian density and a Hamiltonian density. We identified creation operators for the quasi-particle, for the electron. This is known as the Luttinger liquid description of the fractional quantum Hall effect. It was, in fact, originally constructed way before the effect was discovered for a different context, for the context of one-dimensional systems. And it gives us a tool to describe situations where the edge is the main player of the physics.